Good afternoon, or whenever it happens to be that you're watching this. My name is Andrew Skank. I'm a PhD student at the University of Maine. Today I'm going to talk to you a little bit about improved bridge capacity assessment by proxy finite element analysis. So just a little bit of brief motivation as to why we've started this project and we're continuing to develop it. You may or may not know there's a lot of old bridges all around the United States, and particularly in Maine, and they're still being used. They were designed and built in the first half of the 20th century under much smaller design loads than we use today. And that's a little bit of a problem because conventional analysis that we will use to load rate bridges says that these very old bridges should not be able to carry the newer, more modern loads that they do actually carry. The problem is that our experience says otherwise. We know from lots of different testing, just basically watching trucks roll over bridges every day, that these bridges can carry that service load very well without any sign of any distress or damage or anything like that. And so we would really like to be able to have a better picture of the capacity of these bridges, taking into account that, yes, they're a whole lot stronger and a whole lot more resilient than we really give them credit for. So there's a few methods that have come along that do take into account some of this increased capacity. Most notably is diagnostic live load testing, which it has been shown for a very long time to give more accurate prediction of load response. But when we go up to ultimate level loading, we have to rely on linear extrapolation of service level behavior. And that generally doesn't take into account the entire picture. These bridges have very ductile response and they have system level response. And so what we need is a conservative method of analysis that can take into effect the full nonlinear response of a bridge and the full system level response of a bridge. And so that's why we started developing this, what we called Proxy Finite-Element Analysis, or PFEA. So an overview of the general process is three fairly straightforward steps. First is we take a section from a bridge and we extract its fundamental load deflection response. Then we create what we call a proxy section, which is a fictitious section with much more manageable constitutive properties and constitutive relationships that has that same load deflection or load deformation characteristic that the actual section has. And third, we implement that proxy section into commercial finite element software and analyze the bridge, finally getting out a load rating for the bridge by analyzing its proxy. So in a little bit more detail, the first step, extracting the real section's load deflection response. So this particular type of analysis is for slab on girder typed bridges. We haven't tried anything else, but that's the first. It's for slab on girder bridges, and so we've boiled down the most important load deflection response to the bridge's moment curvature relationship, assuming Euler-Bernoulli assumptions, plane section remain plane, all that jazz. But we also take into account the girder section's full nonlinear constitutive properties. The process itself was developed mostly for reinforced concrete, although I'll tell you later that we've expanded it to other types of section. So when we were first developing it, we took into effect the full nonlinear compressive behavior of concrete and the elastic plastic nature of reinforcement, as well as the tension stiffening of reinforcement. So a whole lot of very complex constitutive behavior we pack into this moment curvature relationship. And so the way we get at the moment curvature relationship is we take the actual section, we discretize it, then we subject it to a curvature, and through internal equilibrium, we get the resulting resisting moment for the section when we apply that particular curvature. Then we do it again for a larger curvature, then again, and then again, and then again, all the way up until we have a final material capacity or material failure criterion. And that gives us the entire moment curvature relationship for the section. So then we take that moment curvature relationship and we create our proxy section, which has basically the same relationship except uses much simpler constitutive relations. So if you're looking at the poster right now, you'll see a comparison of an actual section and a proxy section on the middle of the left-hand column there. You can see that they're actually pretty different, but they're also somewhat similar in shape, and that's on purpose. We developed this process for reinforced concrete T-beam bridges, so we didn't want to really reinvent the wheel. Let's make a T. And so when we were initially developing this process, to get a matching moment curvature relationship, we used a genetic algorithm to optimize both geometric and material parameters to get that matching moment curvature relationship. In further development, we found that we can actually just pick a geometry essentially, and the easiest thing to do is not change it the actual section. So take the gross sectional properties of the actual section and use that, and then just use a not a more robust, but a more efficient nonlinear optimization routine to get the material parameters that will give us the same moment curvature relationship. And so I did mention before that we use a much simpler constitutive model. So we just use a combination of perfectly elastic and elastic plastic materials. We sandwich them together and we get finally a moment curvature relationship for this proxy section that matches the real section. So if you see down at the bottom of the left corner, you can see a comparison of the actual section's moment curvature relationship for this particular bridge, the proxy section, and the implementation into commercial finite element software. You can see they match very well, and this shows that we can actually get at a proxy section that behaves very similarly to the actual section, which is what the entire process is based off of. So now we have our proxy section, and we implement it into finite element software. So for simplicity, and because we were more familiar with it, we used the software Abacus, but this can be done with any commercial software, and also it can be done with a self-written or self-made finite element software. It would just take a little bit more work. And so what we did is we used a relatively fine mesh of quadratic shell elements. We made the initially one girder, we tested it and got that it does have the same moment curvature relationship as the actual section. Then we constructed the full bridge model of all the girders, usually 4 or 5 for the bridges that we looked at first, but can be any number. And then we loaded it with HL93, AASHTO's HL93 notional loading, and we solved it with a Rix solver, which is normally used for snapback analysis, but in this case, it just increases the amount of load, until the solver hits a predefined material failure parameter, at which case the solver can't solve anymore, it aborts. But that's exactly what we want. That abort sort of message says, this is where the bridge fails. And so we can get that amount of load, that load proportionality factor, just how many HL93 trucks we've applied before we've broken the bridge. We can take that in a very straightforward manner back into what the actual rating factor of the bridge is. And that's really cool. So a few results of this method so far. So you can see in sort of the middle column of the poster here, we have used the moment curvature extraction process, and we have validated it against lab tests of reinforced concrete beams. So that's the sort of dead center picture or figure there. You can see we've gotten a good match. It's a little bit on the conservative side, but that's what we want. We want a conservative method that can be used for these bridges where we don't have the same amount of certainty of the material properties as we would in the lab. So a little bit of conservatism as compared to a lab test is exactly what we want. So that shows that our moment curvature extraction process is relatively accurate, and it works pretty well. And so underneath that, you can see the results after we've implemented the process for a particular bridge into Finite-Element and into a Finite-Element software. And you can see this plot on the bottom, the middle bottom there. It shows how particular girders, the amount of moment that they carry as that load proportionality factor increases. And you can see that as that load proportionality factor increases, some of the more heavily loaded girders become nonlinear, but they also have their ductility, so they continue to deform as the additional load gets shed to the less loaded girders on the outside. That happens again until finally all of the girders become nonlinear, and so afterwards we have a lot more deflection than finally failure. So that's showing that the process is able to predict that load distribution that we know exists in actual bridges, especially these bridges that we were testing, and it shows that we're getting a good handle on the nonlinear response of these girders. And finally, the chart up there on the top of the right hand shows some of the selected results for 10 bridges, 10 actual reinforced concrete T-beam bridges that we analyzed with this process, that we also live load tested over the course of a few years. So you can see there's an average increase in rating factor for these bridges, which a lot of them didn't rate before. Using live load testing, we had an average increase of 0.31, which is okay. Most of them were raised to above 1.0, so it showed that they're good. However, in contrast, PFEA saw an average increase of 1.04. That is a huge increase in comparison, and that's because we're taking advantage of that full nonlinear response of the bridge and of the girders, rather than just extrapolating a linear service level response. So finally, we've extended the process above that a little bit and to include some new concepts and some new aspects that we didn't actually intend the process to be used for initially. So first, we've reformatted the development of the FEA implementation to actually include and specifically include the effects of skew. So a skewed abutment and it's skewed on how the bridge responds, and we've shown that this skewness and the way we've taken into account is fairly accurate in comparison to our field testing. We've also been able to do ratings for shear based on the results of PFEA. It doesn't have the same amount of sort of big increase that we've seen for moment rating, but it does take into account load redistribution and ductility, so we do get a good bump on shear rating factor through this. And finally, we've extended the moment curvature relationship extraction process to include pre-stressed girder beams. So we've taken our process that was originally defined just for reinforced concrete, and we've expanded it to a new type of bridge, a pre-stressed concrete bridge. So this is showing that we can actually use this for many different types of bridges. There's a lot of bridges that it wouldn't really be useful, or not useful, it wouldn't be a good use of time for, say, a steel bridge, where we have a very well-defined elastic-plastic constitutive relationship, but especially for concrete type bridges where we have a very complex constitutive model, this does get a whole lot. This allows us to get a much better picture of the full nonlinear response of the bridge. So some additional notable usage of the process: we were able to verify the results of the process against results of an actual full destructive test of a pre-stressed girder bridge that was performed in, I want to say, Tennessee in the 1970s. That's that graph you see in the middle of the right-hand column there. And you can see up until the time that the actual bridge failed because of a loss of composite action between the girders and the deck, we had a very good matching of the load deflection response of the bridge. And we actually, looking into sort of the internals of the model that we made of that bridge using PFEA, we actually predicted that it should have failed due to loss of composite action between the deck and the girders, because we were able to get the shear flow between the deck and the girders and found that, yes, the studs should fail. So that's a really interesting and helpful result. And finally, uh, we've actually been able to use the process as evidence for the adequacy of an in-service bridge. So there is a bridge in Maine. It's in the sort of chart there that conventional analysis said was not adequate, and live load testing said was not adequate, but PFEA said was. And so the Maine Department of Transportation took this into account and decided that yes, we're going to take off the load restrictions on this bridge because we accept that this process is based completely just on mechanics and just on very sound uh, concepts. And so they took that into account, and now that bridge no longer has the load restrictions that it had previously, which is a really cool result, in my opinion. So, in conclusion, PFEA is a promising tool for the analysis of existing bridges. It can capture sources of ultimate capacity that are not often accounted for in either conventional analysis or experimental analysis. And it's in line with the straightforward mechanics and conservatism that's generally required for bridge rating. And so it shows a lot of good promise as a method to be used for analysis of underrating bridges in Maine and in the country in the future. So thank you for listening, and if you have any questions, please feel free to email me at my first name dot my last name andrew.schanck at maine with an e.edu. Thank you very much.